Now we see an example which will help prove that the theorem works both ways, that you can see that it either converges or diverges. And so the last one diverges, you can guess this one's going to converge. So we're looking at the summation n equals 1 to infinity of 1 over n cubed. 1 plus 1/8 plus 1/27. So there's on the picture, the dotted line is the function 1 over x cubed, and the dots that hit that dotted line are 1 over n cubed at 1, 2, 3, and so on. So the way that I use this picture to prove that the theorem was going to work is I draw rectangles that are under the curve so that they don't stick out above the curve. Instead, they're missing some space. And their areas are 1, 1/8, 1/27, because they're all exactly width 1. Now, I don't really care about that first rectangle. So I ignore it for a moment and I look at the curve from 1 to infinity. That's what the theorem said to use. And the area under the curve from 1 to infinity is bigger than the sum of all the rectangles after we throw out that first rectangle, or the sum when we would include the first rectangle later. Yeah. So if that area is bigger and it turns out that that area is finite, then so will the rectangles. I won't know what the rectangles add up to, but I'll know that they're finite because they're smaller than a finite number, their total area. So then I do the improper integral 1 to infinity 1 over x cubed dx. Take the limit as t goes to infinity. Antiderivative there would be x to the negative 3 goes to x to the negative 2 divided by negative 2. Plug in the t. It's nice to write it as a fraction, so I wrote negative 1 over 2t squared. And as t goes to infinity, I get a 0. And then that minus minus, so plus 1/2. So I get 1/2. And so that means that the area under the curve is a half, so the summation of the rectangles converges. I don't know what it converges to yet. Now, it did have that extra big rectangle, which was 1, so it could be about 1.5 or 1.5. But all we know is that it's going to be smaller than that, because we know that the 1/2 is really a bigger number. It's the area under the curve, not the area of the rectangles. So actually the rectangles turn out to add up to this number, 1.2020569, not quite 1.5. So you can't determine what the summation converges to. All you can do is know that it converges or diverges using the integral test. Now, those two examples can be done with a variable, and you can see how it works for any value p. So p is going to be a power, that's what it stands for, and it's the summation I equals 1 to infinity 1 over n to the p. So we did it for p equals 1 first, where it was just 1 over n, and then just the most recent one we did p equals 3, so it was 1 over n cubed. But now it actually works out, the integral works the same no matter what value you put in for p. It converges if p is bigger than 1, and it diverges if p is less than or equal to 1. But it doesn't tell you what it converges to. That's a big open question for a lot of these.